Good morning, everybody. How was your weekend? Good. Everyone's happy. Did you have that color of hair before?
Yeah, it was before.
Before, but what it was in preparation for, in support? Yes. Okay. Good. Yeah. How exciting was that? All right. What do we got? This is week 5, and the material from the textbook is chapter 7. So hopefully you've had a chance to look at all that stuff. Chapter 7 is actually going to be, so there's no quiz, and chapter 7 material is not going to be on the midterm exam. So we'll talk a little bit about it today, not too much, because next time we meet, we will have a midterm exam. And that's going to be on the 13th. And the location is to be determined. In other words, it's not going to be in this classroom. It's going to be in a computer lab. Actually, there'll be 2 computer labs. I'm not sure which computer labs yet. As soon as I find out, I will let you know. And hopefully it'll be over in G Hall on the 2nd floor, but it might be in this building on the 2nd floor. So don't come to this location. Because if you do, you'll be late for the exam. So look for that. I will let you know, again, as soon as I find out, or at least before class next week. The material is going to be chapters 1 through 6. So again, chapter 7, which is what we're technically learning this week, is not going to be on the midterm exam. You won't have had any quizzes or homework for chapter 7 due before the exam. So you're going to want to focus on chapters 1 through 6. And let's see, the exam will be done on computer. It will either be through Connect or Blackboard Learn. I'm still working on the details, and but you will have access to Excel, and in Blackboard or the lockdown browser there is a calculator, scientific calculator, so you'll have access to that as well. When I say you have access to Excel, that means you're going to have access to a blank Excel file, and or possibly one that has the, you know, like when you do the quizzes and the homeworks, you click on the link and it opens an Excel file. You're not going to have access to any other Excel files, so you know, stuff you got on your computer or whatever. In fact, you're going to be using the computer in the computer lab, and all you will see is the exam, and then you can, I think you can go back and forth between tabs in the lockdown browser. One of those tabs will have an Excel file. So you can do anything you want with Excel in terms of the functionality that's built in. The probability distributions, we'll talk about some of those today, I expect, when you guys ask questions about homework number 4. And then if you don't want to use that, I guess you can use the scientific calculator. I think it's better to use Excel because you can save what you do, and you can go back and you can look at it and say, okay, this is where I made a mistake, and plug numbers in and see what formulas you called and that sort of thing. With a calculator, as soon as you put the numbers in and you push plus or minus or divide or logarithm or equals, you have no record of what you did. And if you make a mistake, you make a mistake, and it's hard to figure out where that's from. Okay, so there will be between 15 and 18 questions. And when I say that, I mean like on the homework or the quizzes, those types of questions. So some of the questions might have multiple parts, and if they do, I'm counting that just as the same question still. However, when I might have to convert the exam from, and this is all to make Excel work, I might have to convert it from Connect to Blackboard, in which case it will have more questions, but they will be basically the same as what, it'll be the same amount of work as if it were in Connect with less questions. So I would say that at least half of the questions are straight from the homework. So if you can do all the homework questions, then you should get at least 50% on the midterm exam.
So I just said there's questions with multiple parts.
Mm-hmm.
You got like one part from them, the question you found completely wrong, would you get like
yeah, just like on the homeworks and the quizzes, you get partial credit for, yeah. There's 5 parts of the question, you get 4 of them right, and then you get 4 out of the 5.
Is this open up like homework and quizzes, or is it closed notes?
So good question. It is closed notes, closed book, closed everything except for you can have your own formula sheet. And you get 2 sides of 8.5 by 11-inch paper. If you want to put it on 1 page, you can, but you know you got to flip it over. If you want to put it on 2 pages, you can. But if you do 2 pages, 2 sheets of paper, then the back sides need to be blank. You can do anything you want. You can type it. You can write it. You cannot bring a magnifying glass to read it, so don't use like 3-point font and plan on reading it with that. Otherwise, closed everything. So a book, notes, internet, etc. You have to be present in order to get credit. If you try and take the exam from, say, the library or from your dorm room or from any other place, you will get an F in the class and an F on the test. And you won't be able to withdraw or anything like that. So make sure that you are present at the exam. What happens if you miss the exam? Do you need to worry about it? Nope, don't worry about it. Just gear up for the final exam. Okay, so if you got other places to go, other conflicts, they're important enough for you to miss the exam, then focus on them. Put your attention on them. Do what you need to do. Plan on the final exam replacing the midterm.
Where are you posting the location of the midterm?
I will send it out in an email. So on Blackboard, whatever the Blackboard email thing is. Is that good?
Yeah.
Does anybody not get those emails? Okay, question.
I'm not sure if I remember you mentioning if the final is going to be cumulative or not.
Final is cumulative, yeah. Mainly because of the nature of the material. I mean, you can't do the finals once we hit chapter 7, you can't really do that stuff without knowing how to do the stuff before. Yeah, whatever you want. As long as it fits on two sides of an 8.5 by 11 and you don't try and read it with microfilm reader.
So that would mean you only count one grade?
What's that?
If you final in midterm, you only count one grade?
No. I'm not saying that. If you miss the midterm exam, your final exam score will replace the midterm score, not the other way around. So if you miss the final exam, then you're hosed. Let's see, what other questions always come up about this? Any other questions about the midterm? Okay, so make sure you can do the homework, right? The other questions that are not from the homework will be like the questions from the homework. Most likely. Most of them, anyway. There might be a few extras, but probably not. Okay, so a week from today, don't bring your computer, don't bring anything other than, don't plan on using anyway. You can bring, of course, keep it in your bag. Cell phones, that sort of thing, are going to be off limits. If you have like a watch that talks to your cell phone, please don't bring it, or take it off and put it in your bag. Seems like there's something else I'm missing that I should probably be telling you, but I don't remember it. So unless you guys have more questions, yeah, question.
Can we bring our own calculator to use, or do we have to use it on the computer?
Oh, I suppose you can bring your own. That's okay. Yeah.
I know for the first two chapters, is very conceptual. Is there going to be like definition problems in these?
Probably not. Yeah. Look to the homework and the quizzes for the types of questions that you'll get.
Maybe with weird homework problems, like check and uncheck.
Oh yeah, those are. I don't like those. No, those tend to cause problems. I will try to make sure those are not on. Yeah. Let's see what else. Yeah, that's it for now then. Unless you have more questions, feel free to ask during whenever they come to your mind. All right, so let's look at homework number 4. I'm sure there's questions on it. If there's not, then that means you're all doing very well and you should be ready for the exam for the most part. So questions from homework number 4. No one's looked at it yet? This material will be on the midterm exam. Really? No questions from homework 4? All right, well, let you think about that for a minute. Then let's go back to the midterm. What topics do you need to know for the midterm? Well, let's see. What do we start out with? We have descriptive statistics. Those are things like well, I don't know if we should call it measures of center or measures of variation, because those are not just descriptive, but they're also inferential statistics. But we'll just write that down. Measures of center. And what are the measures of the center that we've talked about? We learned about. We have the mean, the median, and the mode. What are the functions in Excel that you can use to calculate this stuff really quickly? And this is another plug I'm making for Excel. Not that I like Excel that much, but average. Isn't it easier just to type average and then point to a bunch of cells in Excel and say calculate the average. The alternative, if you're using your calculator, is to do what? So I'm going to take the average of 17, 14, 12, 8, 9, and 4. Just put 17 plus 18 plus 12 plus 4 plus whatever, and then divide by however many there are. There's lots of room for error when you do that. Median, what's the function? It's just median. Right, so mode, I think there's a mode function. I don't know if you use that one or not. Measures of variation. What are these things? We have the range, the standard deviation, and variance, etc. In Excel, how do we get the standard deviation? It's just stdev.s. That's the sample standard deviation. stdev.p. That's the population standard deviation. So if I know that I have a sample, the question I'm doing says here's a sample from some population. What's the standard deviation? That is S. Formula is the square root of the summation of xi minus x bar, quantity squared divided by n minus 1. And the population standard deviation is sigma, which is the square root of the summation of xi minus mu, quantity squared divided by n. So these things are going to be slightly different. If you are calling standard deviation for the population stdev.p, you're assuming that you know what the mean is, and the mean is going to be calculated as just the summation of all the x divided by n. So it's the same thing as x bar. So these things only differ in the denominator. You have n and n minus 1. So they're going to be pretty close to each other. But the sample standard deviation should be a little bit bigger because you're dividing by something smaller, and then you take the square root. So these are pretty important calculations that we're going to do. Who wants to use their calculator for that? Anybody? Like maybe on Friday night when you're bored, you know, everything else going on. Yeah, I'll just get my calculator out and start pushing buttons. How many times you got to do that? Well, first you got to find the mean, so you got to add everything up, divide by n, and then you subtract that from every data point, square it, divide by n minus 1, take the square root. If you use Excel to do this, it's really quick, and you just push a few buttons and you're done. And not only that, you know where you make a mistake if you make a mistake, because you're calling this function and it gets saved and so forth. Okay, so we have, what else do we have? Measures of center, measures of variation. I think that takes us into probability. Oh, well, let's see. We jumped the gun on that. We've got graphs, charts, and these include things like histograms, bar charts, scatter plots. These are all things that you should know about. other kind of plots do we have? Box plots and dot plots. All these things give us a hopefully a quick visual on what the distribution looks like. In the case of a scatter plot, we're looking at two different distributions, two different variables. So we're looking at a bivariate distribution. And these things, graphs and charts and tables, are also considered to be statistics, descriptive statistics or inferential statistics. In other words, every time I take a different sample from a population, I get a different histogram or a different bar chart or a scatter plot or whatever. Okay, so probability is the study of what? Just remember we talked about that. Probability is the study of randomness, okay, or uncertainty, right? And we said that there's always going to be some degree of uncertainty. If there's not, then life's boring, right? If you know exactly what's going to happen, how is that any fun? Anybody seen a movie they really like lately? No, nobody watches movies. Well, once you watch the movie, you know what's going to happen. Do you want to watch it again? Maybe, yeah. But it's not nearly as exciting as the first time, right? You watch it over and over and over again, you know exactly what's going to happen every single time. Eventually it becomes boring and non-exciting. And so, if there's no uncertainty, then you have just a constant process or distribution, and that's boring. So probability is all about the study of uncertainty, and there's always going to be uncertainty, and we want to understand the uncertainty. What is it that we don't want to try and do with uncertainty or randomness? We talked about it a little bit. We don't want to try and predict it. Why do we not try and predict uncertainty?
Because you can.
Because you can't. Because the very definition of it is it's unpredictable. It's random. That's what it means. You can't predict it. You might get lucky and guess, flip a coin, it's going to be heads or tails. Okay, you might get lucky and guess, but it's not a prediction, it's a guess. And if you get it right, it's luck. Okay, so that doesn't mean that knowing the degree of uncertainty or the amount of randomness there is not useful. It's incredibly useful, and that's what we're learning in this class. But in order to do that, we have to know about probability, and those are including things like experiments, events, outcomes, sample spaces, and all right, so what's an experiment? Experiment's just exactly what it sounds like. You're going to do something and you want to know what the outcome is. So you flip a coin, that's an experiment. You walk across the street, that's an experiment. You wake up in the morning, that's an experiment. Events, those are outcomes. These are the things that result in the experiment. You flip a coin, the outcomes are it's heads or tails. You cross the street, the outcomes are you get across safely or you don't get across safely. Or you get across without getting splashed by a car driving through a puddle, or whatever the outcomes are. We can combine those together to form what we call events. And events then are the things that we're going to assign. We're going to look at those. There are probabilities that are assigned to outcomes, and of course those make up the events. So the sample space, what is that? That's the collection of all possible outcomes. And the probability then we can talk about assigning a number to each of these things. And we have the axioms of probability that says all events have a probability that's between 0 and 1 inclusive, and if we sum up all of the probabilities in a sample space, the sum of those probabilities is equal to 1. And what's the other axiom? If I have probability of A1 intersect A2, that's just the probability of A1 plus the probability of A2 if A1 intersect A2 is empty. And I think based on those three axioms, you can prove any of the laws or any of the things that we've done in probability. And so what are those things that we did? We have laws of probability, including the law of addition, what does that say? That says if I have probability of A1 union A2, well, we just wrote that down as the probability of A1 plus the probability of A2, but we said that's only if their intersection is empty. If it's not empty, then we have to subtract it, and that's the law of addition. The probability of the union is just the sum of the probabilities minus the probability of the intersection. We have things like Venn diagrams. We should write that up here. Those help us understand what's going on with the events and the subsets. We have the law of multiplication, which says if I have the probability of A intersect B, this is the probability of A, let's try like this, probability of B given A times the probability of A. It's also equal to the probability of A given B times the probability of B. And this assumes that the events are not independent. Independent events are the kind where probability of A intersect B is equal to the probability of A times the probability of B. In other words, if A happens, it has no effect on whether B happens or not, and so that's an important law. What else do we have? Conditional probability. Probability of A given B. Well, if you just come back up here to the law of probability, law of multiplication, and solve for the probability of A given B, you see that's just the probability of A intersect B divided by probability of B. And what this says is the universe has changed, B has happened, so given that B has happened, now what's the probability that A happens? And if A and B are independent of each other, then this is just the same as the probability of A, but if they're not independent, then you get law of conditional probability, which brings us to Bayes' theorem, which says I can rewrite this then. Probability of A given B, that's just the probability of B given A times the probability of A divided by the probability of B. Okay, so you had questions on all this stuff in last week's homework, and we kind of went over some of that. Hopefully you're up to speed on how to do this. If not, now would be a good time to ask questions.
Can you just go over, like, one question says 1 out of 30 chances, and like, what
You mean you want to do a Bayes theorem question?
Or just, I mean, I don't know. It's just like an odds. Like, what are the odds? Like, 1 out of something.
Do you have a specific question you can reference?
I don't, but probably like one of the lottery ones. I can get one.
Okay. Yeah. Well, while you're pulling it up, let's do a Bayes theorem question. So let's say that you have say you have a hat. This is a hat. It's a wide brim hat. No, I don't know. It's a bucket. Let's just say you have a bucket that has 3 coins in it. There's 1, 2, and 3. And you know that the probability, you're going to reach into the hat and you're going to pull out a coin. And so the probability that you get coin 1 is equal to the probability of coin 2 is equal to the probability of coin 3. Right? And all of these then have the same probability. You reach in the hat, you don't know which one you're pulling out, but you pull one out. And it turns out that the probability that you get a heads when you flip coin number 1 is equal to 1. Okay, you pull this coin out, whenever you flip it, you're going to get a heads. The probability of getting a heads when you pull out coin 2 is a half. So coin 2 is fair. Probability of a heads given that you pull out coin 3 is 1 over 3. Okay, so you can see the setup here. This is classic Bayes theorem. You're going to reach into the hat, you're going to pull out a coin, and you're going to flip it. And it comes up heads. So given that you have a heads, what's the probability that you have coin, we'll just say coin I for now. All right, because I want to know what the probability is for each of the coins. So I've got 3 coins, I could put I equals 1, 2, or 3. To get this probability, according to Bayes' theorem, we're going to say this is just the probability of heads given coin I times the prior probability of coin I, and all of that's divided by the probability of heads. Okay, so is everybody with me on this? We reach in, we pull out a coin, we flip the coin, it's heads. Now I want to know what's the probability that it was coin 1 or coin 2 or coin 3. My initial guess would have been 1/3. If I pull the coin out, which coin do you have? I don't know. Probability it's coin 1, it's 1/3. Probability it's coin 2, 1/3, and so forth. Okay, so what I need to know here, first of all, is what's the probability of heads? So how can I get a heads? If I get a heads, given that I have coin 1 times the prior probability of coin 1, that's one way to get a heads. Second way to get a heads is if I pick out coin 2, multiply that by the probability of coin 2, plus probability of heads given coin 3 times the prior probability of coin 3. So I know all this information, I just have to plug it in. This is going to be 1 times 1/3 plus 1/2 times 1/3 plus 1/3 times 1/3. And so this is 1/3 times 1 plus 1/2 plus 1/3. And so what is this equal to? This is 1/3, a half plus 1/3, what's that equal to? 5/6. All right, so I get 5/6 plus 6/6, that's 11/6. So I get 11 out of 18. That's the probability of getting a heads. So that's bigger than a half. All right, so I plug this in, I get 11 out of 18 in the denominator. In the numerator, I get, what do I get? Well, I get a third times the probability of heads given coin I. Okay, so let's just plug these numbers in. Probability of coin 1 given a heads, that's going to be a third over over 11/18. And so what do I get for that? Is that 6 over 11? That should be 6 over 11, right? Okay, so what does that say? That says if I pull out a coin and I flip it and it's heads, what's the probability it's coin number 1? 6 out of 11, which is a little bigger than 50%. Right? So before I knew I had a heads, I would say the probability it's coin number 1 is a third. So given that information, I now can update the probability. Given heads, what's the probability of coin 2? Well, that's a half times a third divided by 11 over 18. So what do we get? 3 over 11, so 3/11ths. And I would compare that then to a third here, and 3/11ths is, what is that? So 3/9 would be a third, so 3/11ths is going to be less than a third. So if I see a heads, I would say the probability it's coin number 2 actually goes down. And does that make sense? Well, probability is a half if I have coin number 2 of getting a heads, but the probability of getting a heads is bigger than a half. So so that probability gets pulled down. And so finally, the probability of coin 3 given a heads is going to be equal to whatever's left over, which is 2/11ths. So given I see a heads, what's the posterior probability that I saw coin number 3? It's 2/11ths. Why is that? Because coin 3 has a 2/3 chance of coming up tails. So if I saw a heads, it's more likely one of these other coins showed up. Okay, so that's an example of Bayes' theorem. Now you got to, did you come up? Oh, quite, yeah, here. Go ahead.
Can you go back to so why did you divide that by 3? Is it because there's just 3 coins?
Here you mean?
No, the numerator for the probability.
Which one? This one?
Yeah, why is there 1/3?
Because I've got,
Just because it's 3 coins.
it's this thing right here.
Okay.
All right, it's probability of heads. Probability of heads given coin 1 times the probability of coin 1 divided by the probability of heads. Just, yep. So in other words, I come up with this denominator probability of heads by writing all this stuff out, but all that stuff, I mean, since that's making up the probability of heads, all I need to do is look at which individual component goes with the case of interest. Okay. So was there another question on that? Okay, so you had another question. What was your question?
Well, I just don't get how you do like the odds of something, you know, for it or against it. So like for this problem, it's the probability of being struck by lightning is 0.00045, and it says find the odds against being struck by lightning.
Okay, is that, did I write that down right? 0.00. One more 0. 0.00045. Okay, so L is the event that you are struck by lightning. Okay, and So if you have the probability of some event taking place, the odds are equal to the probability of success divided by probability of failure. So it's going to be probability of L divided by the probability of 1 minus L. And that's the odds in favor of being struck by lightning. So this is going to be 0.00045 divided by 1 minus 0.00045. So that's, this ratio is written as, so typically odds are written as A to B, right? And the probability is going to be A divided by A plus B. So what we're saying is the odds here are going to be 0.00045 to 1 minus 0.00045. Now typically we're going to write that in integer terms. So we got to find integers such that we have not integers, but numbers that you know, we kind of can make sense out of. So let's come over here. Okay, so I guess there's some rounding going on here, but basically what we're saying is the odds you could write as, take the ratio of these things, and so you'd say the odds are 0.00045 to 1, just because this is being rounded, and so if you wanted to go the other way, say the odds against.
Yeah, that's what the.
Okay, so that's odds in favor. Odds against is going to be 1 minus 0.00045 divided by 0.0045, and this will probably make a little more sense if we take that divided by that. We get 2200 to 1. 2200, 221.222 to 1. So those are the odds against being struck by lightning, which are pretty good. You guys remember Star Wars Episode 5? Anyone ever see that movie? They're flying through the asteroid field, and what does Han Solo say? They're coming up on the asteroid field. Han Solo says, "Chewie, set 271," and Princess Leia says, "You're not actually going to go into an asteroid field." And then what does the robot say? He says the odds of successfully navigating an asteroid field are 3,720 to 1. So are those good odds or are those bad odds? They're actually pretty darn good. So they totally botched it in that movie. They should have said the odds of against successfully navigating are 3,721. But what they basically said is 3,720 out of 3,721 times you're going to successfully navigate. Right? So in other words, you could say that we have 3,720 and to 1, So the odds of, or the probability then is going to be this number divided by the sum of these numbers. So 99.97% chance of doing it successfully. Okay, but you know that's odd. So whenever you have odds, you've got to be very careful about the odds of what? Odds of success or odds of failure. Typically, if you're talking about football, when the Eagles played, what were the odds? Anybody know? The Eagles weren't favored, right? So the odds were like 2-1, 3-1, 5-1, something like that. So in gambling, when they talk about odds, they're saying the odds against the team. So the odds for the Eagles were the odds that they're going to lose, actually. So it's 3-1. That means somebody thinks there's a 75% chance the Eagles are going to lose. Right? Because 3-1, you take 3 divided by 3 plus 1, and that gives you probability. Okay. Other questions about that?
I have a question, but I don't think it's the same as this. It's from the homework, like the previous one.
Homework 3?
Yeah.
Okay, let me just write down what it is and we'll come back to it. Homework 3 point. Sorry, what was it?
It's
Question
question 20.
20, okay. So we will come back to that. Let me just mention the other things from probability. We had counting, which included the multiplication rule, which really means factorials, and permutations, and combinations. And we talked about birthdays and guess the secret serial number and blockchains and all that fun stuff. Did we talk? We didn't talk about blockchains, did we? That was my other class. So we talked about combinations. We said, let's play the game guess the secret serial number. Remember that? We said here's a 6-digit number, and you guys try and guess. And whoever guesses it first wins something. Well, that's exactly what's going on with blockchains. You guys have heard of blockchains? It's like, you know, the basis for Bitcoin and these cryptocurrencies, and there's other things out there as well. But what's going on is computers are trying to guess a sequence of numbers, and they're just doing it, you know, as quick as they can until one of the computers somewhere in the world gets the sequence, gets the right number. And as soon as they get that right number, then that is broadcast out to everybody else, and everybody else says, okay, that one's been solved. Let's now find another number that goes with the next block. And these things get blocked together, linked together. And the difficulty with blockchains generally increases with time. And the way they do that is they say, okay, we had a 6-digit number. Let's change it to a 7-digit number. Now you got to guess a 7-digit number. And with Bitcoin, I think they're doing binary. I think it's 30. Right now it's 33 or 34 digits. So basically there's 2 to the 34 possibilities, and you could write them all out, but instead of doing that, computers all over the world are just randomly guessing these things. And eventually one of them gets it. About every 10 minutes, one of them gets it, and then the blockchain is released with some bitcoins. So there's a reward. In this case, 12.5 bitcoins is affixed to whoever it is that guesses that right number. And eventually it's going to go to 2 to the 35 and so on and so forth till it gets to 2 to the 60. And then it's going to stop getting harder with Bitcoin, as far as I understand. I could be wrong about that. But that's the basic idea. So this is applicable in lots of different arenas, and very useful stuff. So now that we know about probability, we talked about discrete random variables including the binomial, the Poisson, and the hypergeometric. And so these will be the topic of homework number 4, and hopefully you guys have decided which questions you want to look at. So let's go back and look at this other one from homework 3, number 20, and then we'll pull up some homework 4 stuff and make sure you guys are up to speed on the homework 4 material. So let's see this. All right, in Minnesota, this is the question you had? In the North Star cash drawing, you pick 5 different numbers between 1 and 31. What's the probability of picking the winning combination? Order does not matter. Okay, so this is exactly what we were talking about just a second ago. So I should have just used your example here. That's all right. Let's throw in a blank page there. So we have homework 3.20. So in the lottery, choose 5 numbers between 1 and 31. So I'm going to write this out. 1, 2, 3. I killed that already. 1, 2, 3, 4, 5. What's the probability of picking the winning combination? Order doesn't matter. Okay, so again, how many ways can I do this? That's the question. And there's only one way to do it right. So we have to know how many different combinations there are of these numbers, 1 to 31, and taking 5 at a time. So how many choices do I have for the first number? There's 31 I can choose. All right. Once I pick that one, I have to choose the second number, but it's not going to repeat, so I know it's 30 is the next, and then 29, 28, and 27. Now if I multiply all those things together, I'm going to get 31 factorial divided by 26 factorial. In other words, what I'm really doing here is I'm saying, let's take all 31 of these numbers and see how many ways we can randomly sort all of them, or randomly put all of them into order. But I don't care about what's happening with the 26 factorial ways that I can do that for the 26 that I'm not interested in. So I'm going to divide that by, let's say there's 26 factorial, I'm going to divide that by 26 factorial because all those things are the same. I don't care about the order of those other ones. But I also need to say, do I care about the order of the 5 that I pick? And it turns out that I don't. So how many ways can I reorder these things? And I'll say there's 5 ways to choose the first one, 4 ways to choose the second one, 3 ways to choose the third one, 2 ways, and 1 way. So this is going to be 31 factorial divided by 5 factorial divided by 26 factorial.
It's also like the order doesn't matter. It's something that all the numbers can be exactly the same. So why wouldn't it be 31 times 31 times 31 times
So it says order does not matter. So I have to pick 5 different numbers, it says, between 1 and 31. Yeah, so I can't have the same number. So in other words, if I pick the numbers 6 and 30 and 25 and 24 and 7. if order doesn't matter, I would say how many ways can I pick that combination? And it's going to be, well, how many ways can I reorder these things? Right, if I wrote 7, 6, 30, 24, 25, that's the same 5 numbers, isn't it? They're in a different order, but order doesn't matter. So those really are the same thing. So when I say I've got 30 times 30, sorry, 31 times 30 times 29 times 28 times 27 ways that I can pick these numbers, that's permutations. That's saying how many ways can I do it where order does matter. So I divide that by the number of ways that I can rearrange the same numbers. That gives me the 5 factorial. So if I come over here, I can say this is homework 3.20, and I have combination, combin. This is a very useful function to know about. 31 comma 5. How many ways can I do that? It turns out there's 169,911 ways to do that. What if I multiply that number by 5 factorial? What should I get? Something that's much, much bigger. Well, it turns out this is the same as saying how many permutations are there when I take 31 comma 5. So if I have 31 objects and I'm selecting 5 of those, how many ways can I do that where order matters? Same thing, whatever that is. 20,389,320. So I want to be careful and ask the question, does order matter or does order not matter? Because if order matters, then it's a lot harder to do this. If order doesn't matter, then there's lots of ways to do it, right? In other words, of the 20,389,320, how many of those have the same first 5 numbers, or the same numbers with a different ordering? Well, I just divide that by 5 factorial, and I get the number of combinations, 169,000. So the question here says, what's the probability of doing that? And so we're going to say we want 1 divided by that number. And I'm just going to copy it and paste it right in here. And it says to round to 6 decimal places, but I didn't round at all. If in doubt, follow their directions and round. And so I got it right. Okay, so is that clear then? All right. Other questions from either homework 3 or homework 4?
So with that question, it took me forever to actually get the answer because it says to round to 6 decimal places, but it was the actual number was to 7.
So just put in 0.
So I put in 0, but I didn't get it, or kept thinking about the wrong answer. So we're not going to put anything like that on the test, right?
Oh, I don't know.
Okay.
Might show up on the test. I don't know.
Yeah. Because I just thought I got the wrong answer. I couldn't.
Yeah. So with the test, you're going to have the opportunity to, go back and check your work, rounding errors, things like that. You can send me an email and we'll look at that. Partial credit there won't be partial credit though. I will have a partial credit like option after the exam, but but rounding errors, those sorts of things. So I'll look at those.
Okay, so that since it has the E on it, so you would just go, it'll be 0 because the 0.6 factor.
So what is this one? This is equal to 5.88 times 10 to the minus 6. That's 0.1, 2, 3, 4, 5, 8, 8, 8, right? So I would count over 6 decimal places. 1, 2, 3, 4, 5, 6. In this case, I would write 0.000006 to get the right number of zeros. So let's just try that. 1, 2, 3, 4, 5, 6. So yeah, I don't want to round that to 0. So that one, if I put 0 in for this one, I think I'm going to get it wrong. Yeah. Again, the easiest thing to do is just copy and paste it in, right? And you're going to have Excel available on the exam, so put. It would take that answer. Yep. Yep. We just did that, right? Copy, paste, and check our work, and it took that answer. Okay, other questions?
We do 1A.
Homework 3. Okay, M&Ms are blended in a ratio of 10% brown, 8% yellow, so on and so forth. How many elements are there in a sample space, assuming the order in which the M&Ms are drawn matters? So it doesn't matter if that is if order matters or not. Same answer. So we have how many different colors? There's brown, yellow, red, blue, orange, and green. So that's 6 different colors, right? Yep, 6 different colors. So we have pairs that look like this. Let's write out the first one can be either brown, green, blue, orange, red, or yellow. And the second one can either be brown, green, blue, orange, red, or yellow. So if I were to write out these pairs, I'd have brown and brown, and then brown and green, and then brown and blue, brown and orange, brown and red, and brown and yellow. So there's 6 ways that I can have brown be the first element, and the same thing with green being first, green and brown, green and green, so forth. So there's going to be 6 ways I can have brown be the 6 ways I can have anything be the first one, and 6 ways I can have anything be the second one. So there should be 36 total ways to do that. Let's check our work. Okay, so other questions from homework 3? Okay, questions from homework 4? Okay, so this one here, lottery ticket has a grand prize of $30.8 million. The probability of winning the grand prize is some really small number. What's the expected value of the lottery ticket? Okay, so the payout is equal to 30.8 million. So that's $30,800,000. Probability of winning is 0.000005. I get the right number of zeros, probably not. It's 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7. Okay, so the expected value of the lottery ticket. How do we find that? What's the expected value mean?
With the probability times the grant price.
So the ticket is going to be worth two values after the lottery. One or the other, right? It's going to be either 0 or it's going to be $30.8 million. So the expected value is going to be the summation of x times p of x. So that's the value times the probability. And so in this case we get 0 times, that's the probability of, 0 is what you get if you lose, and the probability of losing is 1 minus probability of winning. So 1 minus that number plus 30.8 million times the probability of winning. So to get the expected payout, let's come back over here to Excel. This is homework 4.1. We have payout and probability. Winning, so the payout's going to be 38,000,000. Probability of winning is 0.1234567, and so the expected value is going to be equal to 30.8 million times the probability of winning. 1, 2, 3, 4, 5, 6, 7. Okay, so the expected value is $1.54, and the question is, would you pay $1 for a ticket? Now that's kind of a very personal question, isn't it? So what they're assuming is that when you answer that question, that you're going to say, look, if I pay $1, my expected return is 54 cents. Or I should make 54 cents on this investment. That's a big payout, isn't it? That's a 54% investment. I should do that, shouldn't I? I mean, if I were rational and all that. So when you answer this question, don't answer it based on your own personal beliefs about the lottery, or this is not taking into account the risk. I mean, the chances are you're going to get nothing back, right? You're certainly not going to get 54 cents back. You're either going to get $30 million or you're going to get nothing. So let's check our work, and looks like we got it. So I don't know that I really like this part of the question, but should say, would you pay $1 for the ticket if you didn't care about risk? And I mean, because the payout's positive, expected payout's positive, even though your chances of winning are still extremely small. Okay, other questions from, I know there's other stuff in this one that people are going to have trouble with. Yeah, go ahead.
Question 2.
Question 2. I like the pattern I'm seeing here. A statistics textbook chapter contains 65 exercises, 11 of which are essay questions. A student is assigned 15 problems. Okay, so what do we have here? Does anybody know what type of distribution we're going to use for this? So there's 65 questions. how many 11 are essay. $15 are assigned. Okay, so is this looking like a big bowl of candy that has some chocolate and not chocolate pieces in it? No, did you guys watch that video? Yeah, okay, so we're gonna reach in, we're gonna pull out 15 of these things. And we wanna know what's the probability that we get no essay questions. So we'll say X is the number of essays in the sample. All right, so this is capital N is 15. Let's say R is equal to the number of successes in the population. And sorry, this is lowercase n. Little n is the sample size. Capital N is the population size. So part A says, what's the probability that X is equal to 0? And let's back up a second and say, what's the probability that X is equal to any number? And we're going to use what we know about combinations. We just talked about combinations. If I have R successes in the population, how many ways can I choose X of those? Well, it's just R choose X. If there are 11 essay questions, how many ways can I choose 0 of those? Well, there's only one way that can happen. If there are R successes, that means there's capital N minus R failures. And if I have X successes in my sample, that means I have little n minus X failures. So I don't have to just count the number of ways that I can get a success, but I also have to count the number of ways that I can get failures. And then I'm going to divide that by the total number of ways that I can choose little n out of capital N objects. Okay, so this is the probability density function, and I can just plug these numbers in. In this case, I have 11 choose 0 times, what would that be, 54 choose 15 divided by 65 choose 15. Okay, so what's the easiest way to do this calculation? By the way, you get a lot of stuff canceling out when you do this. This is 11 factorial over 0 factorial over 11 factorial times 54 factorial over 15 factorial over 39, I guess it's 30, it's 54 minus 15 factorial. And all that's divided by 65 factorial over 15 factorial, 65 minus 15 factorial. So the 15 factorials cancel out, 11 cancels out, 0 cancels out. So we're left with 54 factorial over 65 factorial times 65 minus 15 factorial divided by 54 minus 15 factorial. So I could simplify it like that if I wanted, and then I could plug in all those factorials into my calculator. Do you think your calculator will handle 65 factorial? I don't know, try it. You got one right there? TI-83? Probably will. What do we get? 8.2. Wait, this is 65? Okay, so we have the denominator 8.24. That's good enough. times 10 to the 90th, and 54 factorial. 71st. Okay. And then we have whatever those other things are. That's going to be really small, right? And then this other thing's going to be pretty big. So you could plug all that in, but my point in asking you that is to say, look, there's a function in Excel that's very nice. It's called hypergeometric. So if I have n, capital N, little n, r, in this case, capital N is 65, little n is 15, r is 11. And I'm going to say, what values of x am I interested in? So there's x, and here's going to be p of x. So x is 0. I'm going to use the function hyper hype geom dot dist, and then it tells me what what my values are. So sample s, that's the sample, that's the number of successes in the sample. That's going to be this x value. Number in the sample, that's going to be this n value. Population, success, how many successes are there in the population? That's r, and the population number is going to be big N. And then do I want this cumulative or not cumulative? What do you guys think? This last one, should it be a 0 or a 1? So I'm saying not cumulative, right? Because I'm just saying probability x is equal to 0. So I need to put a 0 in there. And I get that number, 0.04173. Just to show you, if I take the factorial of the 54, factorial of 65, so those are the numbers that your calculator produced, and let's say factorial of, this is 65 minus 15, which is 50, and this one was factorial of 54 minus 15. And then what did we do? We said this is going to be equal to this number times this number divided by this number times this number. Look at that, we get the same value. So there's the 4.17%. Let's copy it over here, paste it in, check our work, and we got it right. Okay. So my point in showing you this is it's much, much easier to just call this function hypergeom.dist, make sure you know what goes where, and you get the same answer. If you're not comfortable doing that, what are you going to do? You should go and practice it a bunch of times till you're comfortable. That's the best way to get comfortable at something, is practice it. If you're still not comfortable with it, then use the other functions, combination and so forth.
What's the x equal to 0? Is that like the number of successes that you're looking for?
Yeah, so in this question it says, what's the probability that none of the questions are essay?
Okay.
So x is the number of successes. In this case we're saying that's essay, the number of essay questions. Yep. So this is very similar to a binomial random variable. Because binomial would say, look, you either have an essay or a not essay question, and we're going to select how many essay questions. Sorry, how many questions are we selecting? We're selecting 15. So what's the probability that none of those are going to be essay? Well, that's just probability x is equal to 0. But we have a different setup with the binomial. So you got to learn to recognize the different setups. Now, was there a question over here? No, okay. What's the probability that at least one is essay? We're saying what's the probability that x is greater than or equal to 1? and that's going to be 1 minus probability that x is less than 1, which is 1 minus probability that x is equal to 0. So we just have to subtract that value from 1. We'll just put it here, 1 minus that thing. This is probability x is greater than, so capital X is greater than x, in this case plus 1. I'm not going to write that out. I'll just say this is the probability of at least 1. So we'll copy that, paste it in here. Check for work, we got that right. Okay, part C says, what's the probability that 2 or more are SA? So what does 2 or more mean? Two or more means greater than or equal to 2. So this is going to be 1 minus probability that x is less than 2, which is 1 minus probability x is less than or equal to 1. And I'm going to use the cumulative CDF here, the cumulative distribution function. I'm going to put 1 right here, and then I'm going to copy this. Actually, I'm not going to copy it yet. I'm going to, first of all, lock everything except for the first thing. And then I'm going to copy it and paste it in. So the probability that x is less than, or sorry, is equal to 1 is going to be 0.17. What's the probability that x is less than or equal to x? That's going to be equal to, I should have, let's see. Now I'm getting all sorts of numbers goofed up because change that to, oh yeah, no, this is going to work out just fine. I want to make sure I've got the right input value, so I'm going to change this to A23. I'm putting this value for x in, but I need to change this to be cumulative instead of non-cumulative. So the probability x is less than or equal to 1 is 0.21, and that's just the same thing as if I added these two numbers right here, then I get this number here. Okay, so the probability of at least 2 is going to be 1 minus that, 0.786. And we got that right. Okay, so other questions about the hypergeometric distribution?
Just go back to the one for
Here?
on Excel.
Oh, in Excel. Yeah. So this will tell you what the inputs are. So it's x, number of successes in the sample, the number in the sample, number of successes in the population, and number in the population. Okay, so let me do, we didn't take a break yet, did we? So let me just do two other questions real quickly, one on the binomial, one on the Poisson, and then we'll be done for today. Does anyone have a particular one they want to look at for that? All right, here's a binomial question. There's 61% chance that an airline passenger will check bags. The next 15 passengers that check in for their flight. Find the probabilities that all will check bags, fewer than 9 will check bags, at least 9 will check bags. So does this make sense what the question's asking? It says, what number is this? 5. We have n is equal to 15, pi is equal to 0.61. So 61% chance that someone's going to check bags. We're going to look at the next 15 bags, or the next 15 passengers that check in. Part A says, what's the probability that x is equal to 15? What's the probability that all of them check bags? So I could use the probability density function for the binomial, which says n choose x times pi to the x times 1 minus pi to the n minus x, and just plug these numbers in, and I get 15, choose 15, 0.61 to the 15, 1 minus 0.61 to the 0. And I could do it that way and just plug it into my calculator. Most of your calculators actually have this function built in if you have a TI-83, for example. But the easiest way to do it is to do what? Use Excel. So we have n, we've got pi. So n is 15, pi is 0.61, and we have x and p of x. X is 15. What's p of x? The function I'm going to call is called the binom.dist. So binom.dist. X is the number of trials. Sorry, it's the number of successes, and then it goes number of trials, and then it goes probability of success, and then do I want this cumulative or not cumulative? If I put in cumulative, what am I going to get? I'm going to get the probability that's 0, 1, 2, 3, 4, 5, all the way up to 15. I know that's 100% because 15 is the biggest it can be. That's not what they're asking. They're asking what's the probability that all will check bags. In other words, probability x is equal to 15. So I want to put in a 0 here. And when I do that, I get this small number. And it says round to 4 decimal places. I didn't. I got away with it. All right, part B says, what's the probability that there will be fewer than 9 bags? What does that mean? That means x is less than or equal to 8. So I can do the same thing I did over here, but I'm going to say x is 8, and I actually want p of x less than or equal to x. So I'm going to say this is binom.dist. And x n pi, and then I want it to be cumulative, so I put in a 1. If I say cumulative, that means add up all the values from x equals 1, 2, 3, 4, all the way up to the value that I putting in. So I get 35.9% chance that x is less than or equal to 8, which is the same thing as x being less than 9. So at least 9 will check bags. What does that mean? Means x is greater than or equal to 9, and that's just 1 minus probability x is less than 9, which is 1 minus probability x is less than or equal to 8. So we just found out what that was. So we'll just take 1 minus that. And we get 64.5. Okay. Questions on that?
You got the formulas?
To Excel, you mean?
Yes, please.
You got right here. Okay, so let's go ahead and look at one more with the Poisson random variable. And all right, car security alarms go off at a mean rate of 3.3 per hour in a large Costco parking lot. Find the probability that in an hour there will be no alarms, fewer than 3 alarms, more than 6 alarms. So this is number 10. So we're told we've got a Poisson random variable with a mean rate of lambda equals 3.3 alarms per hour. That seems like a lot, doesn't it? Okay, so what's the probability that in an hour there will be no alarms? So part A says, what's the probability that x is equal to 0? For a Poisson random variable, we have the function, probability density function, e to the minus lambda to the x divided by x factorial. And this is for all values of x starting at 0, all integer values starting at 0 and going up to infinity. So if we want to know the probability x is equal to 0, all we have to do is plug into this equation, e to the minus 3.3 lambda, which is 3.3 raised to the 0 power divided by 0 factorial. So this is just e to the minus 3.3, and we can find that so lambda 3.3 and x p of x. So if x is 0, two ways we can do this. First one is to say this is just exp negative lambda, so 3.6%. The other way to do this is to use the function Poisson. Dist, and we put in x. The mean value is lambda, and we want it cumulative. Doesn't matter actually if we get cumulative or not cumulative here, because those are going to be the same. So here we have the same number. One's truncated, but about 3.6% is the probability. Okay, so the next says, what's the probability there are fewer than 3 alarms? Probability x is less than 3, that's the probability x is less than or equal to 2. And so I could say this is the summation, or just plug this number in and get, let's see, we get e to the minus 3.3 times 3.3 to the 0 divided by 0 factorial plus e to the minus 3.3 first over 1 factorial plus e to the minus 3.3 squared over 2 factorial. Could do that. Plug all that into our calculator, or what's the easy way? We're going to come down here and say this is 2. Probability x is equal to 2 is going to be Poisson.dist x comma lambda, and then if I want the probability x is equal to 2, I put in a 0 there. If I want the probability x is less than or equal to 2, of that. This is going to be equal to Poisson.dist x comma lambda comma 1. So I get 35.9%. Okay, so questions on that? Everybody see how I did what I did, why I did it? Okay, so then the last part says, what's the probability that there are more than 6 alarms? I'll just write that out like that. Probability x is greater than 6. So what does that mean, greater than 6? That means 7, 8, 9, 10, 11, 12, 13. Where does it stop? It doesn't stop. It goes on to infinity. Eventually we're adding numbers that are so small that they don't really make a difference. But the easier way to think about this is law of complements. If it's greater than 6, probability of that happening is 1 minus the probability that x is less than or equal to 6. Is that right? Okay, so we've got everything accounted for there. So I'm going to put in 6 right here. And I'm just going to say, I don't care about that part. I'll just do this part. Poisson.dist x comma lambda comma 1. So that's 94%, but I want 1 minus that. So there's the 5%. Come over here, put that in. Check our work. We got it all right. Okay, so questions you guys have? 12b. Okay, software filters rely heavily on blacklists, but such filters typically catch only 33% of phishing emails. Okay, 23%. Sorry, Josh receives 23 phishing emails. What's the chance that a filter would detect none of them? So what kind of, first thing we have to do is say, what kind of distribution are we dealing with here? So you get a phishing email. The filter, this is saying there's a 33% chance it's going to be identified as a phishing email. So this is what type of distribution? Binomial. All right, so this is homework 4.12. Pi is 0.33. And then we're saying if you get 23 emails, so first of all, what's the expected number that would be caught by the filter? Well, 33% of 23. Multiply those together. But part B says, what's the chance that the filter would detect none of them? So probability of it detecting any one is 33%. So we want the probability x is equal to 0. And again, probability of x being equal to x is n choose x, pi to the x, 1 minus pi to the n minus x. So what do we have here? We have 23 choose 0, 0.33 to the 0th power, and 1 minus 0.33 to the 23rd power. So that's one way to do it. The other way to do it is, well, we've already got a kind of a template here, so I'm just going to copy a bunch of this stuff. So this is 12. So now n is 23. Pi is 0.33. And we want to put in a 0 here. So the probability is going to get none of those is very small. So 0.00009. That's a pretty small probability. Okay, so yeah. I will put this, yes, I will put this Excel file on Blackboard so you can check it out. So that's all I've got for today. But let me just say one more thing. When you take the exam, I'm going to implement, well, when I make the exam, I'm going to implement something called random sampling, systematic random sampling. In other words, I'm going to randomly choose some questions here, some questions here. So you might or you might not see all of the topics that we talked about today in our review on the exam, but you need to be ready for all of those. Okay, so don't be surprised when the exam comes around and you don't see something on. I won't give anything away other than that. So we'll see you guys next week. Look for an email that tells you where to come, and enjoy your week.